These days, we cannot live our daily lives without computing devices like computers and smartphones. The history of computers starts from vacuum tubes. Then the transistors were invented, and now we use the integrated circuit chip for computing. These computing units are for the classical computers. But the computer here has a different and unique shape. Inside that silvery cylinder, a very complicated structure exists. The name of this computer is IBM Q System 1. And this is the quantum computer, which is totally different to the classical, ordinary computers that we've seen. In this video, we are going to talk about the quantum computers, especially the qubits. Qubit is the quantum version of bit, so before talking about the qubit, let's first think about the bit. The bit is the unit of the data, consisting of the 0 and 1. For example, 1 for current flow and 0 for no current. Like this, we use lots of bits for saving and processing the data, and huge amounts of bits are needed for our computers. Qubit also follows the similar idea, but has some uniqueness. Quantum superposition and entanglement. It's same that qubit has 0 and 1 states. But like this equation, we cannot decide whether qubit is 0 or 1 before the measurement. This is what superposition is. And we can express this situation with the Bloch sphere. To make quantum computers, like the classical bit, 1 qubit is not enough. We need many qubits for better computing power. Two important features of qubit are superposition and entanglement, which I expressed as uniquenesses before. We already know what superposition is, then what's the quantum entanglement? Let's consider only 2 bits. They are separated, but the state of 1 qubit can affect the other. In other words, they're not connected physically as we think, but they're surely connected. This nonsense phenomenon is called quantum entanglement. The easiest entangled situation is the Bell state. This is the state that the 2 qubits have the same results. If 1 qubit is 0, then the other qubit must be 0 too, and vice versa. We can express this state as phi plus. The 0,0 state and 1,1 state have equal probability. We can make the Bell state by quantum logic gate C0 gate. If we put 0 for the input B, this special gate will give us the output phi plus the Bell state. Like this, by the quantum logic gate, the entanglement can be made and we can use this phenomenon for better calculation. These two features can make quantum supremacy. This word means the state that quantum situations inside quantum computers overcomes the ability of classical supercomputers. We need approximately 50 qubits for pure computation to reach this supremacy. Now we know what qubit is, then how to implement the qubit in the real world. We said that superposition and entanglement are the important features of qubits. For them, the two-level quantum mechanical system is needed. The first example which we can easily understand is using spin. The spin of electrons, nuclei, and quantum dots are quantum mechanical phenomena, and they have two clear levels, spin up and down. The second way to implement the qubit is using existence. The existence of photons or electrons can be used. The 0 state will be the absence of them, and the 1 state will be the existence of them naturally. The absent state is corresponding to vacuum or no charge. Existence will be corresponding to the single photon state or charged state. The third way, which is widely used these days, is Josephson junction. First, let's think about two superconductors. In this situation, they have natural chemical bonding between each other, so-called the strong link. The Cooper pair, which is the pair of two electrons with opposite spins, is the one that gives superconductors some special abilities. This Cooper pair can move freely when there's the strong link between two superconductors. In order to make Josephson junction, we need the weak link, not the strong one. For weak link, we put insulator or non-superconducting material between the two superconductors and form the sandwich structure. In this structure, the Cooper pair cannot move across the two superconductors freely, but it's possible. By the tunneling effect of the Cooper pair, the pair can move to the other superconductor. This tunneling effect can make unique macroscopic phenomena like supercurrents, and this is called Josephson effect. Using this Josephson junction, we can make this basic equivalent circuit for our flux qubit. Now we can talk about which state will be the 0 or 1 in the flux qubit. If the circuit has clockwise current, then it is 0 state. The counterclockwise current is 1 state. With efficient qubits with large amounts, we can make powerful quantum computers. However, quantum computers cannot substitute the classical computers. Therefore, in the near future, we can see the integrated classical quantum computing system to get their advantages at the same time.